Good evening, everyone. My name is Ozgur Sinanoglu. I'm with the engineering faculty with New York University in Abu Dhabi. So tonight's public lecture is actually a part of an ongoing conference that's taking place in this hotel. And the conference is International Conference on Design and Technology of Integrated Systems in Nanoscale Era. So this is a 3-day event, and we're about to wrap up the first day with this public lecture. This conference actually takes place every year in either Northern Africa or in Europe. And this is the 8th time this conference is being held, and it's the first time that we're doing this in Abu Dhabi. I'm the general chair for this year. This is an annual international IEEE event, and this year, this conference is being sponsored by New York University Abu Dhabi Institute. They're the main sponsor and host of the conference, but we also have our industry sponsors, ATIC, Advanced Technology Investment Company of Mubadala. And so it is my great privilege to introduce you speaker tonight, Professor Mark Lundstrom. He is a distinguished professor of electrical and computer engineering at Purdue University. His research is on physics, nanotechnology, and simulation of electronic devices. He's a member of U.S. National Academy of Engineers, and he's a fellow of the IEEE. He has made a big impact in nanotechnology area. He's been the founding director of Network for Computational Nanotechnology, and the associated nanohub.org has more than 250,000 users subscribed every year, and they benefit from the educational services that this network provides. So it's my pleasure to welcome Mark to the podium for the public lecture.
Thank you, and good evening. So thank you for that very kind introduction. I've been hearing a lot about what's happening in electronics in Abu Dhabi for a few years. So when I had a chance to come and see for myself, I was delighted. So it's a great pleasure to be here. Now, I should maybe warn the audience that I'm not often asked to give public lectures. I'll try not to go in too deeply into engineering, but I have a little bit for the engineers. But I won't go overboard in that direction if I can. So when will Moore's law end? What is Moore's law? We'll talk about that too. What will we do when Moore's law ends? So this is a question that is on the minds of a lot of us. We heard it in the first 2 talks this morning. Students are asking, is this an area that I should be preparing myself for a 30, 40-year career? Young faculty that are beginning to establish their research programs are wondering, is this a fruitful area that I should go into? Companies are wondering, what does this mean for us? And society has been transformed by progress in electronics that's been driven by Moore's law. What does this all mean to society? Well, so these are some of the topics that I hope to reflect on this evening. I've been lucky to be part of this for 50 years or so. Since I was a kid playing in electronics, reading my amateur radio magazines, I remember the debates about tubes versus transistors and whether transistors would ever amount to anything. There were real questions in the late 50s and early 60s about that. So just as we can see now the end of Moore's law, it's been predicted many times, but we're pretty sure we see it now. Is it 10 years? Is it 15 years? Is it maybe 20 years? I can also see that there'll come a day when I'll retire. Not immediately, but I'm beginning to ask myself the question, what do I do in this phase of my career as we're looking at the end of Moore's law to make myself useful and to continue to contribute to this remarkable ride that we've been on. So this is an opportunity for me to share some of my own views on where we've been, on where we are today, and where we're heading. I don't pretend to have the answers. I see a few people in the audience that could give this talk just as well or better than I can, and I hope we can have some discussion and share some views. So let's jump into this. So electronics has really shaped the modern world, and it's really transformed the 20th century. When I think back to my days as a kid in the 50s, it didn't seem that long ago. but when you compare what we had then with what we have now, we've been transformed, especially by this field we call microelectronics. And electronic systems, all of these systems are built with transistors. This is the basic building blocks. Many years ago, the number of transistors manufactured each year surpassed the number of ants on the planet of the Earth. They're remarkable. They're everywhere. I remember as a kid when my neighbor, my friend, got a 6-transistor radio. The number of transistors in an electronic system is a measure of the power of the system and its capability. Then I got an 8-transistor radio, so I was the top kid on the block. All right? Then he got a 12-transistor radio. So it's the number of transistors in the system is really a measure of what you can do with the electronic system. The nanotransistor is the first large-scale, true, active nano device, and it's having enormous impact and is going to have even more enormous impact. And this is what I want to talk about today. So, if we stop and think about this, electronics has just shaped the modern world. Beginning with computers and then supercomputers and then personal computers and then all of the personal electronics that we have today. The smartphone is just a marvel that 20 years ago you wouldn't have imagined that this was possible. And communications, weather satellites, internet, all of it relies on integrated circuits. All of it is powered by the transistor. Every year, electronics gets cheaper and more powerful, and we can do more and more. And we've just come to assume that that's going to happen forever. So the idea for a transistor has been around for a long time. So way back in the early 1900s, late 1890s, 1910, 1920, the first electronic devices were vacuum tubes, sort of like an incandescent light bulb. It had a filament, it had a vacuum. It consumed a lot of power. It was fragile. They burned out often. And, it really did have enormous impact at that time in wireless communication and entertainment. But people realized early on that it wasn't the best device that you could think of. It had these problems. A lot of power, it wasn't reliable. So early on in the early 1920s, an idea for a better transistor was patented. Lilienfeld, I believe, was in England. Heil was in Germany. I used to tell this when I first began teaching semiconductor electronics. I would tell my students some of the history. And I remember telling my students, one year about how, these devices could, they were not good enough. They couldn't be made at that time. And then a student came up to me after class and he said, "What do you mean they couldn't be made?" I said, "Well, this is the history that I understand." He said, "Well, I live I'm from California. My next door neighbor is this 90-year-old fellow. His name is Heil. And he tells me they work just fine." Well, they may have worked, but they didn't work well enough to displace vacuum tubes, not for a long time. But progress came along. Bell Labs recognized after the end of World War II that the time was ripe to mount a large-scale effort to build this transistor. These are the 3 people who were awarded the Nobel Prize. They didn't build this transistor. What they did was figure out why it's so difficult to build this transistor. John Bardeen, who won a second Nobel Prize in superconductivity later on, figured out that there were defects at the surface of the semiconductor that prevented this idea from working. But in the process of doing that, they did some experiments and they discovered a transistor effect, and they made a different kind of transistor. And that launched this revolution. Okay, so now this is supposed to be some personal reflection, so I hope you'll indulge me. My first job as an engineer was working for Hewlett-Packard. And at this stage, this was cutting-edge, state-of-the-art technology. And I worked on a process called NMOS2. So things had progressed a little bit, from transistors to integrated circuits. The first integrated circuit technologies were called P-channel. The second integrated circuit technology was N-channel. Electrons move faster, they're higher speed. I was working on the development of a 5 micrometer process we called NMOS2. We now measure the dimensions of transistors in nanometers. So 5 micrometers was 5,000 nanometers. And I can assure you, 5 micrometers sounded enormously small at that time. We had real struggles with making it work. I mean, it was difficult. The development team was 6 engineers. Today, how many engineers does it take to develop a new technology? But we thought it was pretty sophisticated at the time. So what we were on, and we didn't fully realize it, we were on this path called Moore's Law. Gordon Moore recognized in the 1960s that every year, every technology generation, the number of transistors on a chip doubled, and therefore the performance of the system increased, the cost decreased, and we were on this march. This is a plot of Intel data, shows the number of transistors per chip as a function of time. We tend to plot it on a logarithmic scale so that we can see the whole thing. And it looks like a straight line. Every year, every technology generation, which is about 18 months now, the number of transistors on a chip doubles. Our ability to do more and more increases. And when you look at a plot like this, people think, well, okay, it's been going on for a long time. If I'm a young student thinking about what to get into, maybe I can contribute to having this straight line push on a little bit further. And this is what we talk about when we talk about Moore's Law. Here's where I was in my first job, and I can remember those days. One of the things I remember is what it cost. And I remember being told that if you have a manufacturing plant and you have the floor space, it costs you $1 million to convert it into a clean room, and it costs you $1 million to purchase all of the equipment, and you're in the integrated circuit business. So we had 2 fabs in this one Hewlett-Packard plant. Today it costs, $5 billion for a fab? So considerably more sophisticated. Today the questions that we're asking are, my first job was in 5,000 nanometers. How far can we scale? Can we get to 5 nanometers? The area is, shrunk by a factor of 5 squared. So that would get us up to 10 billion or tens of billions of transistors per chip. Almost unimaginable power compared to where we are today. Now, I can also remember, here's 10,000 transistors per chip. I remember being sent to my first technical conference, the International Electron Devices meeting. So this was very exciting. This is when I decided I needed to go back to school and get a PhD so that I could be part of this. The speaker was a fellow named Gordon Moore, who he was well known even at that time, but not nearly as well known as he was now. And I remember the subject of his talk. He said, we are on the verge of being able to put 10,000 transistors on a chip. What could anyone possibly want with 10,000 transistors on a chip? What could you do? Why should we do this? Nobody had a good answer, but we decided all we really know how to do is to put more transistors on a chip. So we'll continue to do it and see if people can find a use for it. And that proved to be the right thing to do. But when you look at this plot, you don't really appreciate what's happening, because this is a logarithmic plot, and what we're talking about is exponential growth in the number of transistors per chip. So this is the same data plotted on a linear scale from 0 to 3 billion transistors on a chip. When you plot it on this scale, you can see that it looks like almost nothing happened until about the year 2000, and then things started to happen. And it doesn't show any signs of slowing down yet. I suspect that if we make this plot in 2020, it will look like nothing happened until 2010 or so. And this is the nature of exponential growth. Once you take one more step, it isn't just one more step in a 50-year sequence. It's doubling everything you've done in the previous 50 years. Each step is just enormously important. So it is very, very important to push this technology just as far as it is physically capable of going. Okay, here's an electron microscope cross-section of a silicon MOSFET. A few years ago, most of them still look something like this. And the device itself, I'm going to talk a little bit about the device itself and then get back to some broader issues. So it's built on a piece of silicon. It has some regions. They're very descriptive. One region is a source. That's where the electrons come from. Another region is a drain. That's where the electrons go out of, and that's why current flows. And in the middle is a gate. So we have a source contact, a drain contact, and we have a gate. And the gate opens and closes and lets current flow or not flow. And if we blow up the heart of the transistor, we see the source, the gate, and the drain, and the region in between is the channel. This is one of the critical links. If you look at this thin insulating layer, this is like glass. This has a thickness of about 1.1 nanometers today. And if you look at the length of the channel, it's about 20 nanometers today. Will be 10 nanometers soon. The question is, can we get to 5 nanometers, 4 nanometers, 3 nanometers? So let me just remind you all what a nanometer is so that we can be calibrated. I'm about 2 billion nanometers tall. Okay. This little dot on this person's thumb is a pinhead size. That's about 1 million nanometers diameter. If you look at the cells, biological cells have scales on the order of micrometers, thousands of nanometers. Now, if we look even smaller to DNA, this double helix of DNA, a double helix strand of DNA has a diameter that's about 2.5 nanometers. Now, atoms, if you line, a hydrogen atom has a diameter, if you can measure it, of roughly 0.5 nanometer. So this is smaller than nanotechnology, but nanotechnology is getting down to these dimensions where nature works in terms of biology and determining the properties of materials. So we're talking about transistors that are the size of biological molecules, and that opens up lots of possibilities. This is the way we draw them when electrical engineers do circuits. There are 2 terminals. Current flows through these 2 terminals in the drain. Well, actually, the electrons flow from the source to the drain, but they have a negative charge, so we draw the current going in the opposite direction. The gate we apply a voltage to turns it on or off. Electrical engineers want to know what current flows when I apply voltages to these terminals. So we look at the current versus voltage characteristics. If the gate voltage is low, the device is off, no current flows. If the gate voltage is high enough, current flows. And each of these lines is a different gate voltage, higher and higher. So there's a region where the current is linearly proportional to the voltage. That's like a resistor. There's a region where the current is more or less independent of voltage. That's the saturation region. And as engineers, we try to understand these characteristics and design them in a way that they can produce useful circuits. And we try to do that for smaller and smaller devices. So my own field has been in understanding the physics and modeling these devices. One reason to do that is that if you understand the physics, you should be able to embody that in a mathematical model, and that shows that you understand it. If you can't do that, there's something that you don't understand. So just the process of the modeling means that you're developing an understanding, and that's needed when you develop technology. But we also need models to do circuit design. And those could be empirical and not physics-based, but it helps if they're empirical. Okay, so a little bit of device physics, and then we'll step back after that. So electrons are flowing from the source to the drain. We apply a voltage. There's an electric field. It pushes the electrons along. If you measure the velocity of electrons as a function of the electric field, we can find how fast they go. The faster they go, the faster your computer runs. Okay. If you apply a small electric field, the velocity is just proportional to the electric field. Double the electric field, you double the velocity. But if you apply a large electric field, the electrons can't go faster than about 10 to the 7th centimeters per second. That's 1,000 times less than the speed of light, but it's still pretty fast. Okay. So this is well known. The pioneers in semiconductor physics knew all about this in the 1950s and 60s. And they developed their models based on this physical understanding. And they were able to describe the characteristics of this device. In the low voltage regime, we have textbook expressions like this that we continue to teach our students. And in the high voltage regime, we have simple expressions that depend on that maximum velocity that the electrons can go at. So you can see already that there are some problems here. We say in this regime, the current is proportional to how wide the transistor is. The wider, the more electrons can flow from source to drain, and how long the channel is. So the longer the channel, the more difficult it is for electrons to flow from the source to the drain. But you can see here what's happening. The length of the channel, due to the progress in technology, is scaling towards zero. In fact, it's getting uncomfortably close to zero. This equation says that the current will become infinite as the channel length goes to zero. Something is wrong, and we're close enough to that limit that we have to go back and rethink our physical understanding of this device. So there's been a lot of work in the 1980s and 90s about trying to understand how electrons flow in these devices. And what you're seeing here are some sophisticated computer simulations done at IBM Research for a MOSFET with a channel length of 30 nanometers. I can remember reading this paper and saying, this is just an academic exercise. We'll never be building transistors that are 30 nanometer channel lengths. Today's state-of-the-art technology is 20 nanometers. Each dot is an electron that is tracked through the computer, mimicking the physics. You can see the vertical axis is energy. Electrons are flowing across without losing much energy. This is what we call quasi-ballistic transport. It's almost as though electrons are flowing in a vacuum, like in a vacuum tube, because the devices have become so small they don't scatter off of anything. If we look at any position here and compute the average velocity, then we can look at the velocity in the source as we go through the channel and out the drain. And if we look in particular at the region near the drain where the electric field is the highest, our 1950s and 60s understanding, 1970s understanding, all the textbooks currently will tell you that at those high electric fields, the velocity is 10 to the 7th centimeters per second, and it can't go any higher. Well, here's 10 to the 7th centimeters per second. What we learned from all of this research is that our understanding of the physics was limited. It's much different in these small devices. An electron that goes from the source to the drain simply doesn't have enough time to scatter. It's out the drain before it has a chance to scatter. So its velocity is much higher than it would be in bulk silicon. Now, one of the issues that I'm going to talk about later is that probably 95% of all the textbooks we use to train people on semiconductor technology still say that the velocity is clamped at VSAT. And we're in this deep nanometer regime. We need to think about how to do better. But there's a mystery, and I'll come back to this a little bit later. This is a new transistor model that's being developed by my colleague Dimitri Antoniadis and his collaborators at MIT. It's called the virtual source model. It is very much based on these traditional models. You simply adjust some of the parameters in those physical models, and you can produce remarkably good fits over a wide range of transistors. So you're seeing here theory and experiment. This is 32 nanometer technology. It works just as well for 22 nanometer technology. It will probably work just as well for 10 nanometer technology. And the question is, how can that be, since we know that it's based on, is it completely empirical? It doesn't seem to be, because you adjust these parameters just a little bit, and you can match measured characteristics of state-of-the-art technology, even though we know what's going on inside has nothing to do with how we derive these equations. Okay, so that's the introduction. I want to talk here briefly now about thinking about this MOSFET in a different way. So a little bit of device physics. So bear with me if you're not into device physics. But we won't go too deeply. And then we'll get back and take a bigger view and think about the future of Moore's law, what electronics is going to be like in the 21st century and how we get ready for this post-Moore's Law era. Okay, so first of all, just a little bit about the MOSFET. So here's what a MOSFET looks like. As I said, it's still a little bit old, but still basically what a transistor looks like. And what I want to do now is to draw the potential energy of an electron as I go from the source across the channel and out the drain. And why am I going to do that? Well, it's because this is a very useful way to understand a device. And I like to quote Herb Kroemer. So Herb received a Nobel Prize in 2000. He's one of the few semiconductor physicists who received Nobel Prizes. He's very quotable. You know, he has all kinds. And this is one in particular I like. When he talks to his students about semiconductor devices, he emphasizes the importance of drawing these energy band diagrams. And he says if you don't know what you're talking about. And his corollary is if you do know how to draw the energy band diagram and you don't show it, your audience won't know what you're talking about. So I'll try to draw an energy band diagram, and you'll see if it makes sense to you, how this device works. Here's the energy band diagram. So this is the potential energy of electrons in the source, in the channel, and in the drain. And we teach students how you draw these energy band diagrams. This is the Fermi level. So this is a little bit of a sophisticated concept, but it's like the fluid level in a lake or jar. The higher it is, the more the states are filled up with electrons. So it's a measure of how many electrons there are there. This is an equilibrium. Nothing is happening. And one of the things I want to remind you of, well, before I do that, is this energy barrier is what keeps the electrons in the source. They can't flow across the channel and out the drain, and current can't flow because there's this energy barrier that stops them. Now, one of the things that we learn in freshman physics is that if you apply a voltage, you lower the energy of an electron. You lower its potential energy because it has a negative charge. Okay. So with that simple idea, we can ask what happens when we apply a voltage. So if I apply a voltage across the terminals, I'm going to lower the energy. So if I apply a voltage to the drain, I'll pull the energy down. And if I pull the energy down, the energy band diagram will look like that. If I design the transistor well, and this is where the engineers spend most of their time, we have designed it so that the potential on the gate holds the potential energy up. The drain pulls it down. We still have an energy barrier. The device is still off, even though we've applied a large voltage across the source and the drain. Okay. Now let's apply a high voltage on the gate. So if we apply a high voltage on the gate, we're going to push the energy down in the barrier. We push the energy down. Electrons can hop over that smaller barrier, get out the drain, and current flows. So that's the way a transistor operates. That's it. That's all there is to it. Now, the details are really, really important, and people work hard on it. But that's it. You're manipulating potential energy barriers, turning devices on and off. So, you know, we can understand these IV characteristics just by manipulating the energy barriers. And this was pointed out by a fellow named Ed Johnson in a really interesting article in 1973, that this is how the device works. And what he was pointing out is that, you know, we electrical engineers get the idea that there are two kinds of transistors. There's a bipolar transistor, which we don't use a lot these days except, you know, RF communications and high-speed internet communications. But the mainstream transistor is a field effect transistor, the one that I'm discussing. Ed pointed out that they're the same device. They operate on the same physical principles. Okay, so transistors, there are really two things. There's electrostatics, which is manipulating these potential energy barriers. And then once the electrons can flow over the energy barrier, it's transport. How fast can they flow? Transport is the difficult part to understand, but electrostatics is the most important part to understand. Okay. So if we look back at this transport, you can see this is called semiclassical transport. Each electron is thought of as a particle, but the nature of the transport can get very sophisticated. About 15 years ago, you know, what motivated me, I was working on other problems at the time, having to do with solar cells and other things, which I'm getting back to a little bit now. But I went to a conference and somebody made the statement that these devices have become so complicated that they cannot be understood. You simply run the computer program and that's the answer, and you just have to accept it. And that seemed like a challenge. You know, we ought to be able to understand these in some physical and yet physically sensible but simple way. Now, I want to point out, and later on in the talk I'll mention this, electrons are also quantum mechanical entities. They're both waves and particles. The wave nature of electrons is becoming very, very important. So you can measure the wavelength of an electron. It's about 10 nanometers or so. We're talking about making 10 nanometer channel lengths. So we have to think about electrons as quantum mechanical entities. So these are some calculations we did a number of years ago. This is the density of electrons. Red is high density. You can see some quantum mechanical effects. The electrons are tunneling underneath the barrier. A classical particle can't go under an energy barrier. It can only go over. But electrons can tunnel. They can reflect off. It sets up quantum mechanical interference. Every major semiconductor company now that is pushing transistor technology below 10 nanometers is developing these fully quantum mechanical treatments of transistors. And I know GlobalFoundries is one of them doing that. So I don't want to talk about those sophisticated simulations. That's what I spent most of my time doing and what my students spend most of their effort on. But what I want to talk about is how we understand what they're telling us, just a little bit briefly. And I like this quote by a famous physicist, Eugene Wigner. You know, a student brought him the result of a computer simulation and said, you know, here it is, the computer matches the experiment. And Professor Wigner said, well, it's nice that the computer understands it, but I want to understand it myself. So that's what we're trying to do. Okay, so I'm still talking about this MOSFET. You know, how do we understand it? So one of the big advances in our understanding of electronics and transport occurred due to Ralph Landauer and people who followed up on his work in the 1980s. And that was a new way of thinking about current. And I'll just mention it briefly here. The basic idea is current is some fundamental constants times something related to the transmission. This is just a number between 0 and 1. It's a probability that an electron that comes in from the source transmits across and goes out to the drain. It's either 0 or 1 or something in between. Times m, and m is the number of channels for the current to flow in. So it's like the number of lanes on a highway. 4-lane highway, you have 4 channels, right? You have channels in silicon or whatever. And this has provided a completely different way of looking at electrons at a molecular or nanoscale. These are some experiments that were done, I think this was Delft, in the late 1980s. This is a thin resistor. It has some length and it has some width that can be electrically controlled. Our classical understanding of current flow is that if you make the resistor wider, more current flows. In this particular experiment, you were able to electrically control the width. The length was so short that the probability of transmission was 1. And the measured results for the conductance, 1 over the resistance, showed this behavior. The conductance generally increased as the resistor got fatter and fatter, but it wasn't proportional. It increased in steps, in discrete steps of 2e squared over h, where e is the charge on an electron. So there was a very simple picture. The conductance was 2e squared over h times transmission times number of channels, and a very physical way was built up. So this led to a fundamental change in how we think about transport. Conductance is quantized. Everything is quantized at the nanoscale. And there's an upper limit to the conductance. It doesn't matter how short you make the resistance or the resistor, you can't make its resistance any lower than this fundamental limit. People have actually done experiments where they put probes on a hydrogen molecule and measured its resistance. It's 1 over 2q squared over h. Right? You can't get any smaller than that. These experiments were done at 4 degrees Kelvin, almost absolute zero in the late 1980s. These effects are now big enough that you can see them in room temperature silicon MOSFETs. And people who are doing careful characterization of 20 nanometer silicon technology these days are paying attention to these effects. Okay, so we can take these textbook expressions and we can adopt them with this theory. And the interesting point is that you can take those expressions which look completely different and you can re-express them in a mathematical way and make them look like the expressions from the 1960s. And you can do that down here at low voltage in two ways. You can replace the length by the actual channel length plus one mean free path. That's the average distance that electrons move before they bounce off of something and scatter. Or you can replace the actual mobility by something we call an apparent mobility. That accounts for the same effects. Up here at high current, the saturation velocity has no relevance in these short devices. But the velocity does saturate, interestingly, and you can relate it to the velocity that the electrons come out of the source at times these factors that have to do with the transmission. So we can explain why these traditional equations work, and we can explain how to reinterpret the parameters in those. So the IV characteristics, and this is something that surprised a lot of people. When we first started going in and saying, let's shut off all scattering processes, let's assume electrons go from the source to the drain and don't encounter anything, just like a vacuum tube, and because that's where silicon technology is heading, let's compute the IV characteristics. Lo and behold, it looks just like a transistor IV characteristic. Most people were surprised by that to begin with. But the reason is very simple. The IV characteristic is determined by manipulating these potential energy barriers. That's what determines the shape. The magnitude is determined by the details of transport. So we can get expressions for the channel resistance. No matter how short the channel is, the channel resistance has a fundamental lower limit that can't be made any smaller than that. And we can explain why, even though the electrons are going very, very fast near the drain, that doesn't help you much on the current because you're limited by how fast the electrons come out. When you measure a transistor characteristic and you see the current increasing linearly as a function of gate voltage, an experimentalist will say, aha, that's a signature that the velocity is saturating. The velocity is saturating, but in a fundamentally different way. It's saturating near the source, not near the drain. Okay, so when we did this, we thought, okay, is this an academic exercise? Does this have any relevance to real technology? And since before I became an academic, I was doing real technology. I've always felt this need to connect to real problems. So what we did is to look at recent technology. Those are the blue dots, measured transistor characteristics, and just lay on top of that the ballistic characteristic for the same device. And what you see is that silicon MOSFETs deliver about half of that ballistic limit. We didn't know how close we were until we did these, and that's actually surprisingly close. And interestingly enough, they operate closer to the ballistic limit under high bias than they do under low bias. Now, there are some other classes of transistors that are used in niche applications for very high performance applications, things like wireless communication, internet communication. These are made out of different semiconductors called 3-5 semiconductors. They have very high mobilities. You do the same comparison with these transistors, and what you find is that these transistors are already essentially at the ballistic limit. So these devices are operating much differently than I think all of our textbooks say they do, and it's important to understand how they operate if we're going to continue to drive these transistors to smaller and smaller dimensions. Okay, so let me not get too much, I think, into the details about all of this physics. I find this fascinating. Not everyone in the audience might be as fascinated with it as I am, but so let me go over some of this discussion of device physics. But one of the things that I just want to point out here is that we can take these expressions developed by a different theory, and I mentioned this earlier, and just reinterpret them, and they look like the traditional theory. And we can do this at low voltage, and we can do this at high voltage. This gives us a very simple physical picture of how this small device works. And the basic idea is that there is a bottleneck near the top of the barrier. Electrons hop from the source into that region, into the channel. And if they can get across that region, they just get swept out and they contribute to current. And the average velocity is related to how quickly they can diffuse across that region or how fast they come in. And the interesting point is that this is an expression that was developed empirically for silicon bipolar transistors in the 1970s, because already the bases were thin enough that these effects were important. Exactly the same expression can be derived, not empirically postulated, and it's needed to understand how these small transistors work. Okay. So a MOSFET, it's just like a bipolar transistor. The region of the channel near the source is just like a base. The high field region near the collector is near the drain is just like a collector. And this explains why you can take these models that were developed in the 1960s, adjust the parameters a little bit, and they work for 10 nanometer silicon technology. And you're not doing empirical curve fitting, but you can give physical significance to those parameters. The reason it works so well is that those first models were developed by some of the best device physicists at the time. They got the essential part of it absolutely correct, the manipulation of the energy barriers. And because of that, the same models that we used in the 1960s are still the ones that we use now and will probably be the ones we use forever. Okay, so those kinds of things having to do with the physics of the devices and their limits are the kinds of problems that I think about. One of the questions that's on all of our minds today is how far can we continue this and what will stop us? Because it is so important to the electronics industry and to what it's doing, how electronics has impact on society. Well, there are many practical considerations, but there are some fundamental ones too. So remember, it all has to do with controlling current by manipulating energy barriers. So here are some quantum mechanical simulations from a colleague of mine, Mathieu Louisier. And these are some results. This is a transistor starting here where the channel length is 13 nanometers. And what you're seeing here is the energy resolved current. It flows over the top of the barrier. Push the barrier down, you get more current. This is the way a transistor is supposed to operate. It's the way these MOSFETs have operated since the 1960s. And they will continue to operate that way down to 10 nanometers. But the questions now are, can we push scaling below 10 nanometers? Can we make the channel length the same size as the diameter of a DNA double helix? So if you go to 10 nanometers, you can start to see the quantum mechanical nature of electrons. They're starting to tunnel underneath the barrier. If you go to 4 nanometers, you can start to see that the electrons don't even know that there's an energy barrier there. It's transparent to them. They just tunnel through. You cannot switch the device off. All right. So this is a problem. And this seems like sort of a fundamental problem. But people are very clever. You know, we used to talk about red brick walls 10 or 15 years ago. And so there were two problems with that. You know, one is it was very discouraging to students. When you say silicon technology is going to hit a red brick wall in a few years, it was hard to get students motivated to go into a field that was going to come to a stop immediately. The other is it wasn't true. The whole history of semiconductor technology is that there have always been impossible problems just a few years ahead. And very bright students have always found very clever ways to address them. And we're not done yet. So here are some simulations from one of our students in my colleague Gerhard Klimek's group. These are fully quantum mechanical simulations that are addressing the question of how small can you make a silicon transistor. And I'm not going to go through the details here, but I just want to point out, you can see electrons tunneling through this barrier and then getting smaller and smaller. And what's happening here is that the student is using different orientations of silicon, and he's using different amounts of strain to change the mass of electrons in the conduction band. And what you would actually want to do is something opposite to what we have been doing for the past several years. You'd like electrons to have a heavy mass. Heavy masses don't tunnel through barriers as effectively. And you can make a 5 nanometer channel length look the way it is supposed to, with the current not tunneling underneath but going over the top. In fact, He's even done this for a 3 nanometer channel length. Okay, and then people say, yes, but this is only a computer simulation. But you know, at these length scales, it's even hard to make a computer simulation of a MOSFET work. So just the fact that you've got a proof of concept, that if you can solve all of the other enormous technological challenges, the basic device can be made to operate to 3 nanometers or 5 nanometers, means Moore's law will continue for quite some time. So, so as I was saying, we're going to be able to continue Moore's law, certainly to 10. The big question now is how far below 10 nanometers can we get? And as I pointed out, every one of those steps just has enormous impact, doubles what we've been able to do for the past 50 years of hard work with every 18 months. So if we can take one more, we need to. If we can take one more after that, we need to. Okay. So there's a little bit of unfinished business here that I'm thinking of. What do we do as this goes along if you're doing technology scaling? One is we really should update the textbooks. You can describe the physical operation of these transistors is simple. It can be taught to undergraduates. In fact, when I wrote my first paper on this, very simple little paper, and I submitted it, the academic review process, and the reviewers beat you up and everything, and it's part of the process, back and forth, you learn a lot. So, one of the reviewers, remarked about this paper is, well, this is a cute little paper. There's only one problem. Any undergraduate could understand this. And I responded to the reviewer, that is exactly why you should publish this paper, because people are making it too complicated. So we really can get, it is not difficult to understand how these small devices operate. It's just different, and we have to get that into the textbooks. Now, we have to push the MOSFET as small as we can possibly make it. Universities have played an important role in this. The FinFET, which is now being adopted by all semiconductor manufacturers as an alternative to this planar MOSFET that I showed you earlier, was invented at UC Berkeley by a team under the leadership of Chen-Ming Hu. But these days, it seems to me that probably the rest of that story will largely need to be driven by industry. Just the sophisticated technology is just at such a stage that it's hard for those of us in universities to be able to do much more there. But there is a question that it is worth thinking about, and this is the one that I think about a little bit, and we shouldn't ignore. And that is there a drop-in replacement? So there's a lot of research these days going on in alternative electronics, spintronics, various esoteric devices, correlated oxides, trying to build switching devices with fundamentally different physics. But sometimes what we ignore is the fact that one of these semiconductor fabs costs $5 billion or so these days, roughly. But that's actually the inexpensive part of it. The design infrastructure that's been built up over the years is just so enormous. What would you do if you had some completely different device, right? We know how to handle a device that behaves like a MOSFET. We have a sophisticated design infrastructure that we can design billion transistor chips, and we know how to do that. If you replace that device with another device, you have to replace it with a design infrastructure that allows you to do that. If you had a drop-in replacement, so what if you had a transistor that gave you the same performance at 0.3 of a volt? Power goes as voltage squared. Factor of 10 reduction in power. Your cell phone battery life is increased by a factor of 10. You could do all kinds of things with a technology like that. Is there anything like that? All right, it's a question that maybe we need to keep thinking about. Okay, so just a word or two about what 21st century electronics will be like. It's hard to forecast, but you have to speculate what's coming. If you read the semiconductor technology roadmap, you see a lot of statements that what's going to happen is that CMOS will be pushed to its limit. You'll have this incredibly powerful technology, and then you'll augment it with other devices that give you other capabilities that go along with that. And we've seen examples, these things that we carry around with us all the time now. You can imagine 20 years ago, if someone would have told you what these things could do, you wouldn't have believed it. And they just have an amazing amount of technology in them. Billion transistor chips, but RF electronics, memory, all kinds of other devices, and we're going to see more and more and more of this. And here's an indication. This is one of these X prizes. $10 million is being offered to a team who can build a device the size of a cell phone that you can carry around, which would do most of your medical diagnostics and monitoring for you. Who knows what's coming, but it's likely to be a hybrid of a basic digital platform with lots of new capabilities augmented by special purpose devices. Now, there are also other opportunities. So there are all kinds of opportunities for innovation and creativity. This is one I like. So there's a lot of talk about personalized medicine, about being able to do cheap DNA sequencing to enable that. And traditional techniques of gene sequencing have been progressing on their own Moore's law at the same rate. So this is just remarkable progress when you think about what it costs to sequence the genome the first time. Then something happened about around 2006, 2007, 2008. The cost dropped dramatically. What happened there? What happened there is that people started asking themselves, how can I make use of ideas and concepts borrowed from silicon technology and repurpose it to do something different? And here's an example that comes from a company called Ion Torrent. So this is an example of where you take traditional, cutting-edge, state-of-the-art technology, which has now produced transistors that have sizes that are comparable to biomolecules. Now you can interface biology with electronics on a natural scale. Couple those transistors to an ion-sensitive FET so that you can read out the charge on the DNA pairs, and you can sequence DNA electronically. And that's ideas like that, this isn't the only one, are driving these kinds of revolution. So there are lots of opportunities for creative, innovation, for students to do wonderful things about taking this remarkable technology that we've developed and doing different things for it. I'll just mention briefly, we're launching a new project in collaboration with the National Science Foundation in the US and the Semiconductor Research Corporation, which is all driven by how do we develop the kinds of SPICE-compatible, compact models for these emerging devices that will enable designers to explore different kinds of applications. So there's a lot of opportunity there. Now, I want to talk a little bit about this new world of 21st century electronics. We hear a lot about multidisciplinary R&D, about preparing our students to work in this environment. Microelectronics then became nanoelectronics, and 50 years of continual progress have produced a technology that has enormous impact. And although we can see the end of Moore's law, we're just beginning to see the impact that this is going to have on our society. Now, one of the things that I'll mention is we talk a lot about silos and about needing to make people broader and about T-shaped individuals, and this is all right, and I believe in this. But one of the things that we sometimes don't give enough emphasis to is how successful this divide and conquer paradigm has been. That by focusing and being able to do a division of labor and having different specialists contribute their own expertise to one problem, we've been able to accomplish an enormous amount. What we need when we do multidisciplinary research is really these T-shaped individuals who have a broad understanding of technology but have a depth in one of them so they can contribute to the multidisciplinary teams. Okay, this kind of thing, 50 years of evolution to a sophisticated technology, has also happened in biotechnology. It's also happened in information technology, and that's been closely related to electronic technology. And it's not quite as far along, but it's happening in cognitive science also. And there's a lot of talk about how these areas are coming together. There's a lot of natural synergies that exploit the connections between electronics, biology, cognition, and information processing. And more, this is where we're going to see the excitement and the opportunities. And students are going to get tremendously excited about participating in this. One of the challenges that some of us have who have been on this path for our whole career is we can see that it needs to continue. But the excitement is going to be in taking what we have and connecting it to new problems in creative ways. We also need those students who are going to push the individual disciplines ahead. Okay, so fostering multidisciplinary research is a big agenda for us as we think about how we educate people. People are also beginning to talk about something beyond multidisciplinary, and they're using the word transdisciplinary for this. It's something a little different. Now, what does this mean? So in multidisciplinary research, you solve problems by getting experts together that pool their knowledge on their expertise, and they bring that together to solve a specific problem. There's a feeling that in the future, there is going to be a much closer collaboration between these different technologies. They won't evolve independently along their own trajectories, but they'll be influenced by their collaborations with others. So transdisciplinary research actually creates new knowledge and affects the evolution of the field, and it can even transcend these disciplines and create new disciplines. And here's an example that I'm familiar with and many of you are. Semiconductor electronics was a new discipline. You know, we had vacuum tube electronics and we had condensed matter physics. And sometime in the early 1960s, a group of people in industry and led by Dick Adler at MIT got together and realized all electrical engineers were being taught vacuum tubes, but the future was transistors and integrated circuits. And they were not equipped to do the innovation and create creative things that they needed to do, because it's pretty heavy going to read Shockley's electrons and holes in semiconductors. So what they did is they got together and they wrote a series of low-cost paperback books called the Seek Notes. We were still using a few of these when I was an undergrad. There are probably a few people in the audience that still have them on their bookshelves. And this allowed, for the first time, faculty to teach this new field. And it did more than that. It wasn't just a simplification of William Shockley's condensed matter textbook. It was a distillation of the concepts into a new field that wasn't vacuum tube electronics, it wasn't condensed matter physics, it was a new field that emerged out of that. And this is the hope, that we're going to be seeing things like this evolve in the future. New disciplines that will come out from intersections between the existing disciplines that we have. And there's a lot of thought being given to how do we encourage this kind of thing. Bell Labs was a particularly successful example of where it was done well. Some of the things they did was to put thinkers and doers together, scientists and engineers, experimentalists and theorists. One of the things that's being discussed with our research sponsors is the need for longer-term research support. Many of the projects that we get are 3 years or 5 years. When you work with a cognitive scientist, it might take you 5 years just so that you can learn how to speak to each other. You're just getting started, and you need longer-term support for these projects in order to foster them. There's a lot of talk about building them, not around how do you take the next step to advance your own personal research, but to build them around large-scale projects, you know, like these X Prizes. Can you do such and such? Build a team and identify a team that does that. But more and more, education, I think, is a very strong driver of this. And I go back to that Seek Notes as an example. And I want to end just by saying a few words, because I'm putting a lot of my time, and my colleagues are, in focusing on education as a driver of 21st century electronics. So one of the things that's guiding us here is that is this idea of simplicity. Can you explain concepts in a simple but sound way? And there's this wonderful story in the introduction to Richard Feynman's famous lectures about someone asking him, why do bosons have spin 1/2, and why do fermions have spin, or why do bosons have spin 1, and Fermi-Dirac particles have spin 1/2? And he said, that's a very good question. I'll think about it, and I'll come back and I'll give you a freshman lecture. He came back in a few weeks and he said, I can't do it, which means I don't understand it myself. So it's very useful to try to think about how you explain concepts simply, because it helps your own understanding. And the other concept is that smaller should mean simpler. So here's an example. This is something we've taught for 50 years. If you take a semiconductor wafer, if you put one probe down that's hot and one probe down that's cold and measure the voltage, you can tell whether it's N-type or P-type. We teach people how you understand all this, right? We got comfortable with it. It doesn't seem so difficult. So then you ask students, what if you take a simple organic molecule with 12 atoms and put a temperature gradient across it? What voltage do you measure? And most people think, oh, this is a very complicated problem. I don't know how to attack that. How can it be complicated? There are only 12 atoms here. There are trillions and trillions of atoms here. It's complicated because we're thinking about it in the wrong way. And, so this is an example I'll mention. We have started to change the way we teach beginning semiconductor electronics. And we started to teach it by understanding small things first and then building up in the course and understanding more and more complex things. So at the end of the course, you get silicon MOSFETs. But at the beginning of the course, you understand how to do this. And at the end of the course, you end up with a much deeper understanding of how things at the MOSFET scale relate to their atomistic structure. And problems like this seem simple. So this problem was actually the homework problem in an undergraduate course taught by my colleague Cipriano Dada for 2 or 3 years before the experiment itself was actually done and reported in Science by a group at UC Berkeley. The students were very energized. This homework problem of ours is now a paper in Science. But it shows you that, that if you look at the problem in the right way, it can be simple. So you hear a lot about MOOCs and these kinds of things today. Our initiative is called NanoHub-U. This is a set of self-paced and live courses that we're trying to formulate to bring some new ways of thinking and new ideas into electronics. So these are short 5-week courses. The idea is that they're serious treatments. They're not watered-down surveys, but they're serious treatments of fundamentals, but they're designed to be broadly accessible. So we attempt to make that if you have an undergraduate degree in science or engineering, you should be able to follow each of these courses without a long string of prerequisites. So it's trying to promote interdisciplinary work. Topics are selected from the most innovative and mature content and the best instructors we have on NanoHub, which we've been doing for a decade. And we're working on this over 4 or 5 years to try to bring some new ways of thinking, a new set of seek notes in. So this is an example. The courses consist of short lectures, quizzes, homework assignments, online simulations that you can do. One of the surprises in all of this is that we find in organizing all of this material that we find it's even more useful in teaching it on campus. We now ask the students to view these on their own time, and we use class time for discussions and problem solving and back and forth. And so there's a lot of excitement in that. This is just an idea of some of the courses that were being developed, and that as resources and time permits, we're doing 2 or 3 of these every semester. And closely related to that is a set of lecture notes we call Lessons from Nanoscience. So this is all about taking all of this wonderful new science we've learned for the past 15 or 20 years in nanoscience and bringing that into the education of engineers. Rethinking the way that we teach traditional topics, keeping much of what we have because it's still enormously useful and relevant, but it's a forum for these new viewpoints to be presented and developed, much like the Seek Notes, designed to be accessible broadly to people with a background in science and engineering. It's a partnership with World Scientific. They're actually publishing these at cost. And so the low-cost paperback volumes are easily accessible by students. And we see this as, every 50 or 60 years you have to stop and maybe think about, are you doing things the right way? And one of the things I've noticed is that a lot of textbooks tend to be written by people of my age, and we tend to write them the way we learned the material. So they tend to look like textbooks 50 years ago. So the whole idea here is that can we get some new ideas and fresh approaches out there that will serve as models to people? Okay, so you've been a good audience. I know it's late in the day and you've been a good audience, so let me wrap up here. So just a couple of points. So I found understanding this familiar device to us from a different perspective as a true nano device is a really useful thing to do. One, for pushing this device just as small as we can make it, for two, kind of an entryway into a whole different class of devices. You take a familiar device, you learn how to think about it in a way that is relevant and suitable for the nanoscale, and it allows you to think about a wide variety of devices in that context. So device scaling is ending. I think we can finally make that prediction. We don't know exactly when, but it's got to come to an end. But for the next 50 years or more, electronics is going to be driven by this incredibly powerful CMOS technology that we've developed, and we've only tapped a small fraction of its potential. Increasingly, we're going to augment this basic digital platform with a variety of new devices. Increasingly, the evolution of electronics is going to be driven by solving society's grand challenges and connecting to electronics, to biology and cognition and other fields. And for people who are wondering, students especially, I'd say that the next 50 years are going to be even more exciting than the previous 50 years. So it's been quite a ride, and it's not at all over. Thanks for the opportunity to share some of these personal perspectives. And I don't know if we have time for questions, but I'd be happy to take a few if we do. Thank you.
Thank you. First, I would like to thank for this really very marvelous talk.
Thank you.
And my question is, besides the geometrical scaling, you also have the problem that you reduce the supply voltage. And you explained nicely how you modulate the barrier to turn off and on the device.
Yeah.
But now you run into problems because of the subthreshold slope. Is there a solution, or is there another barrier?
Okay, so just to be sure that everyone understood, so one of the things that's happened with technology over the years, in my first process was a 5-volt process. Okay. As scaling has occurred, and we've put more and more devices on a chip, power goes as voltage squared. So as we've put more transistors on a chip, we have to reduce the power supply voltage. That worked fine until, what, 10 or 12 years ago or so, and we reduced the voltage to about 1 volt. And now there are some fundamental limitations about the way that MOSFETs work that are making it difficult or almost impossible to reduce it further. So we heard a wonderful talk by Alex today about all of the creative solutions that the system architects are going to do to try to manage power, because it can't be done with device technology alone. When I can't get to sleep at night, I think about, what is a low voltage switch? Is there any way that we can beat this 60 millivolt per decade? It's proving to be very, very difficult. There are ideas like band-to-band tunneling transistors that operate under different physics, but they don't deliver us the speed that we need. You don't want to give up on that idea, but it's a very challenging one. We're still hopeful that there's a creative answer out there. If we could find a way to reduce the power supply voltage from 1 volt to 0.3 of a volt, that's a factor of 10 reduction in power. That would just have enormous impact. Yeah.
Thank you.
So we mentioned the scaling and making the channel shorter. We also covered supply voltage. But one of the things that actually sometimes we tell students about is really not energy, not performance, but really the energy efficiency. Like how many computations you can do per unit energy. Mm-hmm. And there is actually a curve similar to Moore's law called Coulomb's law, which is plotting, the computation per unit energy, for the technologies from the vacuum tube all the way to the nanoscale. Mm-hmm. And this actually also exponential. Mm-hmm. And so can you comment about, the energy efficiency aspect of future technologies? Do you think we'll keep, this exponential growth in terms of the energy efficiency of our computations?
There's not much that I can say about that because it's not my field. It's sort of the hope of those of us on the device technology side of things that the system architects and people who understand, you hear people understand, how do I redesign algorithms so they flip as few bits as possible? Because every time I flip a bit, I dissipate some energy. There's a hope that a lot can be done at the system level, and that a lot of that drive in continued energy efficiency will have to come from system-level considerations because we can't reduce the power supply any further unless we have a device technology breakthrough. And that's an enormous challenge for us.
Okay, thank you.
Thank you, Professor. You mentioned that you are trying to make the freshman science or BS student to understand your theory. I think it's even more important for the social scientist to understand your theory, right?
Yeah.
Theohart's vision of new sphere is realization of your vision on a global scale. I don't know whether you think that it's important also for you to teach social scientists on this thing.
Yeah. So I do, and I guess you're very fortunate in New York University to have a strong liberal arts emphasis. So you have the science and the liberal arts embedded, and you have wonderful opportunities to do that. I'm seeing, when I'm on panels doing various studies for the National Science Foundation and things like that, more and more we're having social scientists and cognitive scientists and people from other fields participate, people who are thinking about the implications of this technology and what it means to human society. So I think in the education of engineers, we need, these technologies have reached the point where their impact on society is so profound that we as engineers and teaching our students, we need this good, strong humanities core and the interaction with the social sciences.